Hello and welcome to this year's lecture on the finite element method in theory and implementation. My name is Wenzel. I'm from the Institute of Scientific Computing here at TU Dresden. My assistant is Veit. He will also help you with the tutorials and the assignments that will follow later on. And firstly, I'm glad to hear and see that so many people are actually joining this course this semester. And we have so many different backgrounds here from mathematics, from engineering, and from other branches of science. So I will try to make this a suitable course for everyone. And whenever there is problems with the topics I'm talking about, and whenever I should address certain things more precisely, then please always come forward and let me know what I can do to help you. So let's start with the beginning. Let's start with the introduction. What do we actually want to talk about in this course, and particularly today? So at first I will give a short introduction and tell you about the organization of this course. Then we talk about what's FEM, what does the finite element method actually mean, and why would you need it for anything? Why are you actually here in this course? Then let's talk about more precisely about some problem settings and then how you get to a solution from that problem. Then a particular point that is relevant because so many people here in the audience are actually from an engineering background. So I want to give a short distinction between the term FEM in engineering and in mathematics. So of course with a higher focus on what it means in mathematics because that's what we are doing here. Then the next point on the agenda is the structure of a finite element software in general, which will also be the structure for our lecture this semester. So we will more or less, at least in the beginning, follow the construction of this software, and this will also give the guidelines for our agenda in the lectures and tutorials. And then as a last point, Python as our tool of choice. So we will do all the coding in Python this semester. Because we have decided that it is one of the simplest and also most powerful and most modern languages there are. And we will give a very, very, very short beginner's guide in this lecture and also in the follow-up tutorials. So talk about environments, how you get there, what the data types are in Python, how you do some standard stuff like loops and conditions and numerical computations. This is very rough and very short. And for everyone who has worked with Python before, more than just half an hour, I can say that you might also skip this part of the lecture and go straight ahead working on the assignments and tutorials, because this part might actually not be new for you. Now let's get started with introduction and organization. Firstly, we have to answer the question, who are we? So who is the Institute of Scientific Computing? It is an institute that's part of the mathematics department, and our location is the Willersbau. So a very old, as you can see in the left-hand photo, a very old building in the middle of campus. And if you look from right in front of the building, you see that up here on the right-hand side, there is our institute. So, as you can see here, the Institute of Scientific Computing, so that's what we are doing, computing stuff for science. More precisely, who are the people that are in charge of this course? The head of the course is Professor Axel Vogt, who is also the head of the institute and the head of the mathematics department. The lectures will be given by me, as you can hear. My office is in the Willersbau on the second floor, B211. So if you have any questions, my door is always open. Of course, you can also email me or ask questions on any other way. And the assistant of this course, who is responsible for everything related to tutorials and assignments, is Veit. He has an office 2 doors down from mine. And of course, if there's questions about those topics, just ask one of us, so we can always help you, and we are glad to help you. All right, because this is a special situation and you are not sitting in front of me in a lecture hall, but you're listening to me digitally. We also have to, of course, talk about digital platforms. So as you have probably already noticed, there is one platform called Selma that belongs to the TU Dresden in general. So this is used for registration for courses and also later on registration for the exams. So please, if you haven't done this yet, look up what Selma is and register for this course there. Then there is Opal. So Opal is the e-learning platform of TU Dresden, and we will extensively use this for the publication of the lectures and the assignments, also handing in the assignments. So it is very important that you also register on Opal for this course. So if you go on the Opal page and look for this name, you will find our course, and please just click on enroll for the course, choose one of the tutorial groups, we will talk about this later, and then you are good to go for this course. But probably most of you have already done this, because otherwise you couldn't be listening to me right now. Then the next thing we need is Matrix. So Matrix is a chat client that is provided by the university. So the servers for this chat client are actually TU Dresden owned. So we have created a chat room for the course for questions that you might be asking and that might be relevant for everyone. And of course also the possibility to write a direct message to us, because that's usually faster than writing an email. The link to the Matrix room is also found in Opal, so you can just click on it and then you're good to go. And the last thing we need is BBB, that's short for Big Blue Button. That's a video conference system also hosted by the university. And we use this for the tutorials, so for the part of the teaching that is not done by recordings. The idea of BBB is that it is all browser-based. So you don't need to download any particular software, and you can just click on one particular link for a meeting that we will publish in Matrix, and then you are part of the video conference. So short notes about the lectures. They will be published on Monday, every Monday on Opal as recordings. And we have a short division into the first and second half of the semester. So the first half of the semester will be preparation of the implementation. So as you probably have guessed, we are a course with high focus on applications. So what we actually want to do is build our own finite element software. So the lecture will firstly serve to prepare those things. And in the second half of the semester, I will give you an overview of the theoretical background, so more or less answering the question, why does finite element method make sense? Then also at this point already, but I will do this again later, I want to recommend another lecture given by the mathematics department, and that's called Numerics of Partial Differential Equations, or in the German abbreviation PDE-NM. This is given by Professor Oliver Sander and his assistant Patrick, and they are doing very strongly related topics to what we are doing here. So more or less, they are giving you all the theoretical background that can be done in terms of finite elements and numerics for partial differential equations. And what they're also doing is they are also introducing a very powerful finite element framework called Dune. And I think this course fits very well to what we are doing here, because while we set up our completely own finite element method, completely coding everything from scratch, they are doing the two other parts. So they are focusing on, firstly, the theoretical background, and secondly, also the use of a pre-coded framework that can be used for finite elements. So I strongly recommend taking both courses, because it will also help for our course to know the contents that Oliver and Patrick are doing. But of course, it's not mandatory, it's only a recommendation from us. Then about the tutorials, there will be two tutorial groups. One is on Tuesday at 7:30 a.m. The other one is on Wednesdays at 11:10 a.m. They are given by Veit, my assistant, and me. And as I have already mentioned, the platform is Big Blue Button and we post the links in Matrix. Everything else about the tutorials will be explained in the first meeting, which is this week on Tuesday. Then, of course, everyone is curious about assignments and exams. So we have decided to give assignments to you every week. And those assignments are supposed to be completed at home, as in a preparation of the next tutorial. The reason for this is that coding in general is something that you can only learn while doing it. So I can explain 10 times how you would implement a certain part of the software, but you will only actually understand it when you do it yourself. And because that takes too much time to do it in the tutorial, we want you to at least work on this at home. So the topics of those assignments are application of the contents that we discuss in the lecture and tutorial. So over the semester, we actually build our own finite element software. As the format or the tool that we use, we have decided to use Jupyter Notebook. So that's a very handsome framework to use Python, because as you will later see, if you haven't worked with this already, it can combine assignment texts and also code directly without doing too much effort around it. Assignments can also be submitted to us. That is, of course, optional, but we recommend this. So if you have completed a particular notebook that is one assignment, then you can also hand this in Opal. We will talk about it later, how you actually hand this in. And if you have completed an assignment correctly, then this gives you bonus points for the exams. So it is actually rewarding not only in terms of understanding the topics better, but actually in terms of also getting bonus points. And then in the end, the exam is it's a written exam at the end of the semester, and we will probably get dates in March. I can already tell at this point that people enrolled in mathematical master programs, you can come forward if you don't want to participate in the written exam. For you, it's also legitimate to ask for an oral exam, but we can discuss about all of this later on. And then the exam, of course, takes care of the contents of the assignments, the tutorials, and the lectures. But already here I can say that the focus of this exam is also on the applications. Now to the next question. What is FEM and why would you need it? The answer to the question what the finite element method actually is not so simple, but I'll try to summarize it in a few words. So the finite element method is a numerical method that uses computational resources to approximate the solutions for partial differential equations. The long answer, what FEM actually means, will be given in the rest of the semester, because that's actually what this course is about. And now to the other part of the question, why would you need it? Let's look at some applications. So you see here in this spreadsheet some ideas, some keywords. So of course it's probably known that finite element methods can be used in engineering or physics. That's something you might have heard of. So for example, like some heat transfer problems or fluid flows, that's pretty standard. But then there is also other applications, for example, in medicine or in biology. And that's one of my research projects. That's why I will go into this a little deeper at this point now. Let's look at this video. What do we see in this video? We see a couple of cells that have been, so like actual biological cells that have been plated in a confined environment, and you see them moving around. Of course, it's interesting to look into the movement patterns of cells, how they behave. And then, well, looking at this video, what do the mathematicians do? Well, they look at it and they analyze the behavior, and then they set up a certain model for it. And for example, what we have done is we have set up a partial differential equation model that sort of describes the behavior, or that resembles the behavior of those cells here. And although this looks a little cryptical, what we have written here, we can see that if we actually use then, on this of course a little complicated model, if we then actually use the finite element method to simulate the results, we get something that looks actually a little similar to what is happening on the left-hand side. So the bottom line of this slide is the process of analyzing an actual phenomenon of nature, describing it in a mathematical model, and then solving it using a finite element method is a very powerful task, because the one thing can only be observed in experiments and the other thing can be done purely in a simulation. So some of you might have heard the name finite element method in a different setting. Especially in engineering, people also use the term finite element method when they are actually talking about something different than the things that we are talking about. And it's not precisely different in the essence, but it's different in the way that these things are presented. So on the left-hand side here, you see a framework. So you see some beams and you see forces acting on them. And in engineering, you would call this problem a finite element problem, because then it gives you the actual load on these individual nodes here and the deformations and so on. So that's FEM in engineering. And then, although this sounds rather intuitive, people in mathematics do this stuff on the right-hand side. So they throw around different Greek letters, and then they write weird formulas, and then they have these weirdly shaped meshes and things that are doing stuff. So it looks much more complicated, but in the essence, there are similarities. And although I don't want to go into detail about the differences and similarities, I just want to mention at this point that sometimes you might stumble across the name finite element method and you see something described that looks quite different from what we are doing here. Don't be surprised, those things can actually happen. Our focus in this course is on the mathematical perspective. So during this course, we want to actually try to find out what this means. So what these letters mean, how we can actually do the whole setup of the software, and how we can use the FEM to solve some of our problems. Next step, structure of a finite element software. And that's also the agenda for this semester. In order to not confuse you too much with all the weird mathematical expressions, I will start off with something that is not actually the finite element software, but instead the model. So let's look at this blue brick that we see here and imagine this is made of metal. So let's say we have a rectangular shaped metal brick. And what do? Well, we heat it up on one side to a constant temperature of, let's say, 100 degrees. We isolate it on all other boundaries. And we ask the question, what's the temperature at a particular point of this brick 1 second after the heating is turned on? So this question might sound simple, but it's actually not super trivial to find out what the temperature is. So what's the step that we do next? Well, we want to set up a mathematical model. So we put this all in a more quantitative way. And we say, all right, this is a three-dimensional object. And we call it omega. We call it omega because it is the domain that we are interested in. So whenever in this course I use the capital omega letter, You can think of a rectangular shaped brick of metal or some other material where you want to consider certain things happening. Inside of this brick, we use a conservation law that's written here, saying that the time derivative of our quantity u, so u meaning in this case our temperature, at a certain time and point. This is also the only time in this whole lecture that you will see me writing an arrow above the x variable. So usually it's self-explanatory if I mean the x to be a vector or to be a scalar. So in this case here, in distinction to the t, I'm writing this vector arrow, but this will probably be the last time. So the time derivative of our quantity u is given by the Laplacian of u, so the sum of all second derivatives. Why this is a conservation law and why this makes sense is something that I will not discuss at this point because it would take a little too long. So what it essentially means is that over time our quantity is spreading equidistantly. Okay, so that's one thing. And the other thing, of course, are the boundary conditions. So we have said that we want to heat up our brick to 100 degrees at one side and isolate it on all other sides. What does it mean to heat up the brick? It means that our temperature is set to a constant 100 degrees at the left side. So precisely at all points in the boundary of omega, so that's this delta omega here, that's the boundary. So all parts of the boundary of omega where x is equal 0, which is essentially just this left side here. There we set u to a constant value of 0. These boundary conditions where you actually set the value of the function are called Dirichlet boundary conditions. And then on all other parts of the boundary, so essentially points in the boundary where x is larger than 0, we set the gradient of u times the normal derivative, so n is the outward normal of the domain omega, meaning that it is always a vector that at every boundary point is pointing outwards, is equal to 0. What does this mean? This means that we require that there be no flux of the quantity u in outward direction. So tangential flux is no problem because then it means the quantity is just diffusing on the inside of the domain. But outward flux is supposed to be set to 0. And this is in the model precisely what isolation means. Okay, so now you have we have derived a model, we have some partial differential equation, we have some boundary conditions, and we want to solve it. And here in this model, you see that there are different problems that we have to address. The first problem is we have to explain our computer what omega is. So the first order of business, try to capture omega in your computer. And although this is quite simple when talking about a brick, it is not that simple if you talk about a more complex geometrical shape. So firstly, the domain. The next part is try to explain your computer what a function is. Computers don't understand functions in that mathematical sense, but they only understand numbers. So we kind of have to represent functions, in this case the function u here as our temperature, in a way that the computer understands it. And then of course we also have to factor in those derivatives here, and then we have to capture the boundary conditions. So there is different problems that we have to address in this semester. And if we have addressed all of them and solved them, then we can actually build our finite element software. And if we do that, FEM gives us results. So what I've done here in this image is I have implemented this conservation law with these boundary conditions in a finite element software. So one that we could, essentially one that will be written in this semester. And then I have visualized the temperature profile. So on the left here, you see the constant 100 degrees. On the right here, because we have started with a 0 degrees brick, so here it's 0. And then you see that there is a decay of temperature from left to the right. And after a certain time span, you can see a profile like this, with the heat diffusing from the left side to the right side. So, to summarize what I just said, we start with a model. The model might be a heat equation like the one we just saw in the example. It might also be Navier-Stokes equations describing fluid flows, or something even more weird like the things I have shown you in the biological examples. But we start with a model. Then there comes the finite element method, and what parts belong to a finite element method. Let's see. We have a grid. So the grid is essentially the component of the FEM that deals with our domains. So how do you describe a brick or a more complex shape in the computer? Then there is the basis part. The basis part is, although this might sound cryptic at this point, we will dive into this a little more into detail in further lectures. So the basis is essentially the part of the software that gives your computer a way to handle those functions. Then there is the next part, quadrature. Quadrature is a term for numerical integration, because we will see in the course of this semester that for finite element methods to be implemented, integrals occur naturally. And of course, if you have an integral and you can't solve it explicitly, you have to do numerical integration schemes. So that's where quadrature comes into play. And then, of course, there is also time discretization things, because we have seen that this heat equation was a time-dependent problem, so that's another part of the software. And then, if you have all of these individual parts, they again form your finite element method, and this gives you a solution, like the one we have seen in the example before. So the task of this semester is to implement all of these individual parts, and then in the end combine them to get a solution for a problem like the heat equation I've shown you. Now, as I have already mentioned before, we have chosen Python to be our programming language of choice. And at this point, I want to give you a very, very short introduction into the programming language. And as already said, all of those who have worked with Python before can also skip this part of the lecture and go direct to the tutorials that will follow up, or to the next lectures next week. Okay, firstly, some of you might ask, how can I actually use Python? So you might have seen some tutorials or something, how a Python syntax looks, and you're curious what the setup actually requires. Well, lucky for you, the setup of Python is quite simple no matter what operating system you are running. If you have a computer that features Linux, some type of Ubuntu distribution or something else, then I can say that Python is shipped with all major Linux distributions. So executing Python files is doable right away. And other necessary packages can be installed from the command line using the tool pip. That's the Linux Python package manager. In macOS, it's also shipped inside the kernel, so Python is also usable directly. And if you want to install additional packages, my recommendation is to simply go for Homebrew, because there you can also install every package that you require by simply executing a single one line. And in Windows, there is different ways. So the simplest way on Windows is to get a distribution of Python. So one program that wraps a lot of Python packages in one. And the most famous distribution of Python is Anaconda. That's also the one I'm recommending, because in Anaconda it's quite simple to install additional packages and to also change your Python environment. So that's my recommendation. If you want to go for the more professional way, it's of course also doable to download and install Python from their website. And then you can use pip in the Windows shell for every other operation. As I'm personally not much of a fan of the Windows shell, I would not recommend this way, and I would simply get Anaconda. But that's completely up to you. For every further question about the setup and the environment, I recommend you to just look at one of those many tutorials that you can find online. So it's a very common thing you can just Google it and find explanations on all the setups that you might need. Okay, another side remark at this point: when I write necessary packages, I mean precisely 3 packages. The first one is NumPy. That is a very, very basic and standard package in Python, and it's usually already shipped with the distributions. So NumPy is the numerical Python library. So that's used for all vectors and tensors, numerical computations. So that's exactly what we need here. Then another necessary and quite powerful package is the matplotlib, so the matrix plot library. That's used for visualization, so that can be used in any fashion you can imagine in creating beautiful plots. That's also something we want to have here, because we have to somehow visualize our results. And the last thing that is not super standard is Jupyter. So Jupyter is an extension that features a combined environment of programming and writing. So you can, if you look at Jupyter and Google it, you can open or create notebooks that have parts of written text and parts of programming environments. And because this is a super simple and elegant solution, that's why we're using these for our assignments. So we will essentially distribute one notebook per assignment, where the assignment tasks are already filled in, and the only thing you are left to do is actually fill in the code blocks. So that's those 3 essentials when I talk about necessary packages. Let's take a quick look into data types, because that's something fundamental for every programming language. Of course, you have these standard data types also in Python. So we have integers, and we have floating point numbers, and we have strings. And what you see here is something that is quite different compared to, for example, C++ or Java or other higher programming languages. You don't explicitly define I to be an integer and X to be a float or S to be a string. You just have an assignment, and derived from the data type right of the equal sign, you assign the data type of the variable I. So if in one line I would have I equal 0, and then in the next line I would write I equal 1.5. So let's do this. So I write I equal 0, and then in the next line I write I equal 1.5. I have not redefined the data type explicitly, but implicitly I have done this by assigning the value 1.5. So after this execution, I is a floating point variable, so it's not an integer anymore. This is, on the one hand, beautiful, because you can redefine and redeclare all variables that you need, and you save a lot of effort and a lot of code. But it's also, of course, dangerous. So sometimes you actually might have to be careful with the assignments, because if you write something of a wrong data type on the right side of an equal sign, you won't get an error message. It just will do the wrong thing in the execution process. So just be aware of this and be careful. So you see an example here. I assign two variables, I equal 1, j equal 2, and then I give a print statement of I plus j, and then automatically, because I'm adding one integer and another integer, the type of the result is also an integer type. By the way, what you see here, these are screenshots from Jupyter Notebook, so when you run Jupyter for the first time, you will recognize that this looks quite similar to what I have shown here. Of course, if I assign floating point numbers x equal 2.0, y equal 4.0, then I can also do other operations, and then because those two are floating point numbers, my result 0.5 is also a floating point number, so nothing surprising happening here. Okay, after talking about those standard data types, we will have to look into a few slightly more complex data types. And the very essence of Python is the list. So a list is a combined data type where you can write more than one variable in there, and they are denoted by using the brackets. So whenever I write some data into brackets, I'm automatically creating a list. What's beautiful about lists is that they are well suited for dynamic storage changes, meaning that I can add something to a list easily, and this is a very efficient operation. The reason is that you might have heard this before in some fundamental programming course. Lists are always stored in a way that every element points to the next one. So if I have this list and I simply want to add something to it, I can just do this. So lists are quite flexible. That's why it is very useful when we don't know the size of the data when starting the computation. Typical operations are append, that's what I did here, and pop, which is the opposite operation. Okay, see here a few lines of code. I've created a list with the elements 1, 2, and 4. Then I have executed the append statement with the number 7 and printed the contents, and little surprisingly, I have 1, 2, 4, 7 here. Of course, pop can also be done. So what happens if I use the statement pop is that I take out the last element of the list and return this. So my list is 1, 2, 4, 7 after I have executed my append statement here, and then I'm executing pop and assigning the return value to the variable I, and then I has the value 7. That's the one that's printed here. Okay, but you can play around with this quite a lot. The next important data type that we need here are arrays, more precisely NumPy arrays. An array is more or less the opposite thing in terms of usability of a list, because in a NumPy array you always fix the size. So you automatically have to say that my NumPy array has a fixed size by creating it from a list of a fixed size or by creating it as zeros of one particular size. The advantage of NumPy arrays is that because their size is always fixed, it is super efficient to do numerical computations, and you can perform all types of operations that you can imagine super fast. But of course it's difficult to change the size. So those two data types, lists and NumPy arrays, they go great together because whatever your use case is, you can find the one that suits them perfectly. In here, in the example, I've created two arrays, and then I have executed the plus. So the beautiful thing is that I can just write a plus b, and I don't have to explain to Python what this plus means. It automatically does a component-wise adding. What you see here is that in order to do this, I had to import NumPy first. The reason is that NumPy, although it is a standard module, it does not belong to the core of Python. So whenever I want to use it, I have to import it first. And usually it's common to abbreviate NumPy by NP, such that in all further statements you can simply write np.array instead of addressing the full name numpy.array. Okay, so now we have seen standard data types and lists and NumPy arrays. Now let's go to two other standard things in programming languages, loops and conditions. So the for loop, as the most famous type of loop in Python, is always defined with respect to a list. So Python syntax always requires you to say for my variable name in a certain list. So as you can see in the example here, I've written for variable I in this list, and then in each iteration of the loop, I'm printing the value of I. So I is taking all values in this list and then printing them. What's also quite common if you want to use the typical for loop that's counting from, let's say, 0 to a certain number, then you would simply write for I in range of, and now of course if I want the 10 to be included, I have to write 11, because in Python indexing always starts at 0 and excludes the last one. So range of 11 is 0, 1, 2, 3 until 10. Also important, at this point you can already see that in Python the indentation is important. So if I want to emphasize that this part here is the inside of my for loop, this indentation here is necessary. So I write for something, then the colon operator, and then an indent here. And if I want to include an if statement, that can be done pretty easily. So if my number I fulfills a certain condition, then I want to print it. And you see, not very surprisingly, it prints only the numbers 3 and 4. What you see here is also that there is an additional level of indentation, because now this one here is for the inside of the for loop, and this one here is for the inside of the if clause. You can play around with this a little more, but this is the rough idea of it. Okay, then now just a few remarks about numerical computations and visualization. From my experience, whenever you want to use a certain numerical operation, no matter how complex it is, it's always a good guess to first look if it is already implemented in NumPy. So there is so many functions already existent in NumPy, and they are usually implemented quite fast and quite efficient, so it's always the best guess to just use them. So what we do here is we create two vectors, and when I say vector, I mean precisely NumPy arrays. And then it's just a one-line statement to compute the means of this vector. That's 2.0. That checks out if it's 1, 2, 3. The mean is 2.0. Then I can also do the adding. We have seen this before. I can do a summation of all elements in an array. That's done here. If I write the star operator, this is automatically a component-wise product. You should always be aware of this fact. So what I get here is 4, 10, 18 because, well, you see it like this. And then the last one I've shown here is the dot, so resembling the actual dot product, so the scalar product of two vectors, and that's multiplying the components and then summing up. But also, of course, NumPy is capable of doing much more, so we can also handle matrices, so higher order tensors. We can sum up the elements of a higher order tensor. We can find out all those places where components of A are bigger than 5. So this in here is a Boolean statement. If a component of A is bigger than 5, this gives me true, otherwise it gives me false. If I'm summing up over those Boolean statements, the true is counted as a 1 and the false is counted as 0. So I have 6 places where components of A are actually bigger than 0. That also checks out, 6, 7, 8, 9, 10, 11. And then if I want to form a matrix vector multiplication, the NP dot of A and V gives me what I would expect from a matrix vector multiplication. So this matrix times this vector. In order to create a higher order tensor from lists, you see here that I had to use double brackets for nested lists. So the inner lists are in row direction, the outer lists are in column direction, meaning that this matrix A has the form 3, 4, 5, 6, 7, 8, 9, 10, 11. That's A. Okay, there is so much more you can do with those numerical computations, and you will get used to this throughout the semester, but here just a rough idea. So it's a very powerful tool, these numerical computations, and they will be of a huge help for us. Now let's look at visualization. I've already mentioned that the tool for visualization is matplotlib, and there is countless ways to do plots in two dimensions or 3 dimensions. It's a very powerful tool, and what's perfect is that NumPy and matplotlib go great together. So a great way of putting data into your visualization tool is to use NumPy, and that's what I've done in this example. So first up here, importing both things. So firstly NumPy, and then also the module pyplot of the matplotlib, abbreviated by PLT. Then I'm creating a vector x as a linspace. Linspace means that I take values from 0 to 1 with 100 steps. So 100 equidistant steps between 0 and 1. So what x actually contains is 0 and then 0.01, 0.02, and so on until 1.0. Then I'm defining another vector here that's called y, and it is x square. So the double star is a power operator and x square. And then I'm simply calling plt.plot of x and y. So the x vector in the x direction and the y vector in the y direction. And then I call plot plt.show to actually show this plot here. And we see that in only 4 lines of code, I was able to plot a function. And of course, it would also be simple to plot the sine function or an exponential function or anything else you can imagine. It's super easy to just do these computations and visualizations in Python. That's all I'm going to say about this so far, and everything else related to the implementation parts will be done in the tutorials and also learning by doing throughout the semester. So I hope that you are satisfied with the choice of programming language. And I think for everyone, even those of you who are not used to Python so far, you will appreciate the fact that you get used to it, because it's a very nice thing to know this language these days. All right, a few final statements. Let's talk about the next important dates. So what's on the agenda? Firstly, of course, our tutorials. So our tutorials start this week on Tuesday, October 27th at 7:30 a.m. Or if you choose to do the other tutorial, it's Wednesday, October 28th at 11:10 a.m. Please choose one of those tutorial dates in the Opal course, so there is enrollment for one of those dates, because that makes it easier for us with the organization. Those tutorials are given on Big Blue Button, so it's also important for you to join the matrix room before the actual date, because there those links will be provided to you. The topics of these tutorials in this week are Python basics, so we will actually try to apply the basics that I just talked about. And then next week we have another lecture, of course. This will be uploaded on Monday, November 2nd. And the topics are finite difference methods. So finite difference methods, sometimes called the small brother of FEM, because they are also a way of numerically solving partial differential equations. And they are simpler, but also a little less flexible, I would say. And because it's easy to introduce, I've chosen this to be the first actual lecture of the semester, because there you can actually see the process of defining the whole method in a single one lecture. And then at this point again, I want to mention the other course, Numerics of Partial Differential Equations by Professor Sander and Patrick. And if you want to join this course, I would also recommend you the OPA side of them. They also provide their BBB links there. The lecture is on Monday, today, at 11:10 a.m. And the first tutorial is on Tuesday, so tomorrow, October 27th, at 9:20 a.m., so after our tutorial. And what they are doing in the tutorials is a further introduction into Python, and they set up the environment needed for this more complex and more powerful FEM software that I promised you already. So I thank you all for your attention and for listening to me, and I hope to see you in the tutorials and also in the lectures next week. And then, yeah, thanks a lot and until soon.